right? It's always the case. Yes, yes, sir.
When you do the trick, x minus x naught plus x naught, so is the purpose of that so you can find a form in which you can use like the Maclaurin series?
Yes, the reason I'm doing that is all about I'm trying to center it at 1, and
or whatever the center is.
Yeah, yeah.
So like, because if you didn't do that, you'd have to like write out each derivative and then find the derivatives.
Yeah. So, and again, it has been pointed out for that example that wasn't really like you could just do Taylor's theorem and evaluate that one. It's not that bad, right? Mm-hmm. But here, let me show you another one. Actually, are there other questions? Since I have burnt too many valuable class minutes on this problem. Yes? And have deprived you the joy of finding the solution yourself, too. No, I'm the worst. Problem 106. Wait a minute, no. Example. What example am I on? 4, I guess. I'll make it 5 just to be safe. How about this? What if you had something like e to the, I don't know, x. I think we haven't done anything like this, have we? I don't think I have anything like that even in your homework, but how would you do this? Take the log of both sides. That's very adventurous. I don't know what I would do. I'm not sure what I would do with that, though. Interesting, but I'm not sure if that helps. So how about this? This is e to the u, right? Which is 1 plus u plus 1/2 u squared plus dot, 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 right? But what is my u? What's that? Cosine. So u is x plus minus what? 1/6 x cubed, 1 over 120, x to the 5th, and so forth, right? In other words, your u is 2x minus 1/6 x cubed plus dot, 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 right? Now, there's hope for this making sense. Why? The reason there's hope for this being a reasonable calculation is that there's no constant term in my substitution. As a general point of order, if you're trying to do something and you find that your substitution has a constant term in it, and you're taking a series where you're taking a constant plus powers of x and summing those powers, that's not, it might not be wrong what you're doing, but it's not helpful because you're going to have to sort through how this infinite series of constants somehow coalesces into your constant term. All right? So I warned about this like 3 days ago, but you might not have been ready to hear it at that point. Maybe you're still not ready to hear it. That's okay. But this is 1 plus 2x minus 1/6 x cubed, right? Plus dot, 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 1/2 2x minus 1/6 x cubed squared plus dot, dot, dot. What would the next term be? If I want to go to order 3, do I need to include the next term? Actually, I think I do. And the reason I do is because why? (2x minus 1/6 x). I mean, this is where it gets dicey. Yeah. You have to think about how can I get, like, as you go up here, what's the lowest order term? Well, let me just talk about down here. I have 1 plus u plus 1/2 u squared. So let's just talk about this term by term, the thought process, okay? What are the orders that we're encountering here? It goes what? Order 1 to, 1 and up, right? And above. This one goes order what? Greater than or equal to what? Yeah, 2 and above, right? This one? 3 and above, right? Because if you think about taking a cube of a sum of things where your lowest power is x, then that lowest power gets multiplied by itself 3 times. That gives you the x cubed, if you think about foiling it out. So what I have then is I've got 1 plus 2x minus 16x cubed. And when I multiply this out, what do I get? I get myself a 4x squared, right? This times this gives me 1/3, but I have 2 of them, so I get minus 2/3 x to the 4th. Actually, I don't care about that. All right, and then plus 1/6, and then I get 2x times itself. Okay, so everything else that I'm not writing down has order higher than 3. And I've already wasted my time and written 1 order 4 term, right? So, okay, we'll get rid of that in the next step. So what do I have? 1 plus 2x. And how many order? I get what? Plus 2x squared. And then what else? Order 3, I've got what? Minus 1/6 here. What's that? 8/6. So we get what? Plus 7/6 x cubed if I haven't made a mistake. So there you go. I mean, this is a way you could calculate the first 4 non-trivial terms in the Maclaurin series for this function, right? My point to you is that composition of series is actually a meaningful calculation as well. But I don't think I've really assigned you any of these, have I? Not, maybe not. So don't worry. Yep.
Could you repeat what you said about your warning for the constant in front of something?
Yeah, let me see if I can. It's better if I can illustrate by trying to do something and having it like work out like that, and then you know what I mean. Like, let me see if I can think of a place where that. How about? Oh, here's one. Suppose I'm looking at f of x equal to 1 over 2 plus x, right? And I want to find the Maclaurin expansion for that. Some of you might think to do the following. Well, this is 1 over 1 plus x, right? So I can think about this in terms of a geometric series. I can think about r equals to minus x plus 1, right? And so then this is the sum, n equals 0 to infinity, all right? Minus 1 to the n times x plus 1 to the n. But if I'm looking for a Maclaurin series, if I'm looking for the series centered at 0, I'm not done, am I? See, because what I have to then do is FOIL this thing out, right? To make it more explicit in the plus dot dot notation, what this looks like is 1 minus x plus 1, right? Plus x plus 1 squared minus x plus 1. Let me write it 1 plus x rather, okay? That's just, I don't know why that just helps me more communicate what I'm saying here better. See, each one of these has a constant term. If I'm after the Maclaurin series, right, I'm trying to eventually simplify this to what? Like, you know, a constant plus c1x plus c2x squared plus dot dot dot, right? So every single term there is contributing to the constant term, to the linear term, to the quadratic term, eventually to the cubic term, to the quartic term. It's horrible, right? So while this is correct mathematics, right? Like, this is a legit application of the geometric series, no doubt. It's just not helpful. What should you do instead? You factor 2 out, right? And you learn that, in fact, this is the sum n equals 0 to infinity of like 1/2 minus 1 to the n. Oh, well, let me see. Blah, blah, blah. I'll get it eventually here. Minus 1 to the n divided by 2 to the n plus 1 x to the power n, right? Like that's the Maclaurin series for this thing. So it turns out, when you collapse all that stuff down, eventually you get to 1/2 minus 1/4 x plus 1/8 x squared, and so forth. But to understand that you got a half here, I'm not entirely sure that even can be seen here. I think we might actually be slightly outside the applicable. See, actually, this is worse than what I'm saying. Why? Why is this worse than what I'm saying? I said that this is a legitimate application. It is a legitimate application for what? The absolute value of r less than 1, right? But what is that here? You have the absolute value of x plus 1 less than 1. Does that include 0? Oof. It does not. So actually, no amount of simplification here will even get me to the Maclaurin expansion. So this is the, but that's the kind of thing I was trying to get at. You want your expansion to be what you're aiming for, not just because you can do it. Yeah.
Could we do something with like binomial expansion?
Oh, out of time. But what's that?
Binomial expansion, like the 1/2.
Oh yeah, you could, yeah, indeed, you could use binomial theorem to expand these, but even so, you'll never,
More difficult than what
well, it won't even work, because this expansion does not apply at 0.
Does binomial have like a if
Is there a formula for binomial? Or,
like a plus x to the alpha? Like that's what I'm talking about.
the binomial series?
Yeah.
Well, yeah, but that still has to have the form 1 plus u to the alpha,
Oh.
and so it's got that 2 there. That 2 is the problem. You got it.